Hello, people on Crowdcast who have just joined us. Sorry, it took us a minute to go live on Crowdcast, but now we're talking about computational tractography and the challenges of it, and developing a standard and community-based file format for it. Let me just jump straight into the alphabet soup of different file formats that already exist out there. And these file formats evolved primarily through the development of software to do computational tractography. People doing this, visualizing computational tractography, innovated and created a variety of different file formats that suited their use cases. And each of these formats provides a different set of trade-offs to deal with the challenges of dealing with very large collections of polylines. So that's one challenge. There's just a lot of different formats. So if you're trying to write software to do this, now you have to think about, okay, which formats does my software produce? How do I interoperate between formats if I want to work with different software tools? And that's tricky. And then each user has to sort of consider the trade-offs of each one of these formats and try to make sense of that. Another sort of problem beyond the just basic interoperability of multiple file formats is that this doesn't have none of these have a clear relationship with other standards and best practices. For example, BIDS. So BIDS has, prescribed a standard file format for volumes, for surfaces, for metadata, for tabular data, but none so far for tractograms. Although there is a draft in progress that tries to square that circle a little bit. So those are all challenges. And what we are proposing, or proposed in the past actually, and have been sort of continuously proposing, is a community format for tractography, and that would be a new file format. In addition to that alphabet zoo, we can talk about why that might be a good idea if you want, and there's plenty of discussion that we've had in the past. The goal is something that would harmonize existing features and functionalities from these previous file formats, identifying strengths and weaknesses of these previous file formats, and taking the best from each as much as we can. The goal is to create a file format that would facilitate data sharing, data reuse, avoid duplicated efforts or wasted resources, increase compatibility, interoperability between software libraries, between different projects. And then really a goal that the thing that really started all this is the real need for improved computational and data storage efficiency, ways to reduce the footprint of these data files and make the practical use of them easier and better. So a little bit of the history of this. The file format that we call now TRX or T-Rex, depending on if you're me or Francois, is it started really in a discussion on GitHub. It really actually started in a mailing list in the Neuroimaging and Python mailing list when the developers of the NeBabel library were contemplating what to do with funding from the Chan Zuckerberg initiative in developing this, and Franco, who's sitting here in front, raised all these problems related to tractography and the need for improvements on the current state of affairs. That migrated then into GitHub and became a conversation that really identified all of these challenges. There are all these desiderata here in these colored boxes. We want computational efficiency, compatibility, I/O speed, limited disk use, and so on. And looking at the existing file formats, it looked like you can pick 4 of these maybe in the best case, and that's what you get. So the discussion went into kind of considering the existing file formats, their strengths and weaknesses, and the need for all these things: uniformization across tools, features that the field needs, simplicity, conceptual simplicity, and we'll talk about that when I'll show you what this file format looks like. It is, in our mind, conceptually simple, and then really all these performance requirements like memory, robustness, speed of I/O, and then we wanted this to be something that doesn't belong, quote unquote, to a particular project. This ideally would cross different communities of users, different software implementations, different approaches to analysis and or creation of these streamlines and analysis of these streamlines, not something that is like the X file format where X is a particular software project. And extensibility, of course. So it became a long discussion here. So here's the whole sequence of things that happened from there. There was this original mailing list conversation migrated into a GitHub discussion, which then evolved into a community-edited Google Doc where people really started hashing out the details of this file format, and eventually became a GitHub organization under which there is a specification repo that's language agnostic of what this file format is. It's a one-page document, so it's really, that's nice in the sense that it really specifies this file format in few words, really, and the hope is that it's complete. But if it's not complete, if there are ambiguities, then that's something we need to fix, and you can help us. And then there are, under this organization, several language-specific implementations of input, output, conversions, and so on, in Python, in JavaScript, in C++, and even in Pascal, thanks to Chris Rorden's efforts. The Pascal in particular. The others have touched others of these things, but Chris Rorden is entirely responsible for the Pascal implementation, I have to say. And so this is what the file format is in kind of in a picture. The idea is that the file format is a directory. It's a directory that it's like many other file formats, like the Word doc file format or Excel file format. It's actually a directory that stores multiple things under the name ohbmdemo.trx. So first of all, it stores some metadata and header, and then information about the streamlines, the offsets to individual polylines, and the positions, the three-dimensional XYZ positions of the nodes of or the vertices of the polylines are stored in two big binary blobs. In order to facilitate the saving of disk space, all of these binary blobs that are saved inside of this file specify their data type clearly in their name. And that's so, for example, the offsets, maybe you want to store them in integer file, an integer 64, maybe for some reason you need 64 bits of precision for these integers specifying the offsets. If you want to save space, maybe you just go down to 32, 16. You need to say what you've done there. Same for the positions. You might want to vary the precision, and you can get trade-offs of precision and disk space that way. So that's at the top level. Inside of that, there are data per vertex, data per streamline. There's the option to specify groups and data per group. This is in order to facilitate what was identified in the discussion as a need not served by any of the existing file formats, which is the ability to specify within a collection of streamlines which streamline belongs to which group. This is this work that a lot of people are doing in the research, is to identify groups of streamlines as belonging to certain entities inside of the brain or things of that sort. So that groups and data per groups came from that. Data per vertex and data per streamline are features that exist in existing file formats, but are currently not as efficient and disk space saving as they can be by, for example, modulating the precision with which different things are saved and specifying them. So you can imagine saving, for example, data per vertex, which is a color X, Y, and Z in several different binary files. FA can be sort of one binary file here, but you can also consider, for many use cases, you can consider the need, and that's specified here, for three-dimensional kinds of properties, either per streamline or per vertex. Often we need three vectors, and those are specifically highlighted by the fact that the blob itself is saved with a 3 in its name. So all that kind of specifies how you can use the underlying data. And then because it's saved in this way, maybe this is here, yes. So advantages of this kind of organization, it's a straightforward specification that covers a really wide range of use cases, although I'd be eager to hear if there are use cases that are not well covered by this. It provides a simple human readable in this way, that if you open the directory and you look at it, you can see the file hierarchy, but it's eminently machine readable as well. You can provide data type per data for each data per streamline, data per vertex, and that provides potentially pretty dramatic disk space saving. And then in terms of efficiency of computing, you can access, it provides random access to memory maps of the data, and that provides highly efficient memory use without a lot of cost in terms of computing time, and that's because access to parts of the data can be as efficient as possible. That was identified early on in the discussions as a real need. Often those of you who have worked with these kind of files, you sit there, you have a 10 gigabyte file with lots of streamlines in it, and really you just want like those 100 streamlines. So this facilitates to some degree that, and then provides a novel and straightforward way to group streamlines into groups and bundles and specify properties of individual bundles or individual groups of streamlines within that. Maybe I shouldn't highlight too much of the novelty. You could just save a lot of different files if you want. That's what we do currently. Last year at OHBM, we first presented this as a poster that was co-authored by many people who participated in the original discussions, and we presented this roadmap for development of this file format with, say, the ultimate goal of inclusion in the brain imaging data structure standard. And so where are we with respect to that? So the idea was to have discussions, proof of concept in several different programming languages, a little bit of scripts to work with this thing, and then start working on incorporation into a variety of different tools by today, basically, with the goal of getting community input, community review, have some conversion scripts, and then by, say, next year, OHBM have this be formally in bids and also in the software implementations be in such a shape that it can be used across really a wide range of tools. So where are we? There is a Python implementation that is, 99.9% authored by Francois Rowe, and is full-featured, and it includes both input-output for these kinds of files, but also converters from other file formats, scripts to convert between existing file formats and this file format as well, which is helpful. There's a JavaScript implementation, primarily due to Chris Warden's efforts, that at this point includes really fast input-output in JavaScript for this thing. So those are the two implementations that really are, you can download these and use them today if you want, and try them out and convert files that you have and see what that looks like, how it feels, how you can save space with that, how benchmark performance of various algorithms that you're using to see whether it provides good speed up and so on. I'll come back to the C++ implementation in a minute, but let me just say that we've ourselves been trying to do exactly that, benchmark it, try it in various use cases, across a broad range of different things. So first of all, there's work within the diffusion imaging Python library to integrate TRX input and output into the library, and because of that, we were then able to integrate TRX, or at least start benchmarking TRX-based pipelines in work that we're doing on this library called PyFQ that does bundle identification, segmentation in tractograms. That sentence is not finished, but implements the TRX-based pipeline for what I just said. So we have started kind of proof of concept in benchmarking, although I don't have like very clear results yet on like speed up or disk saving yet, because it's still very much work in progress. And then, so that's one set of use cases. Meanwhile, the NeView library, again, Chris Rorden and others are working on this library for visualization of tractograms in JavaScript, already provides the ability to visualize TRX files. So I'd say maybe we're something like this. We have some, I'd say, incorporation to debabble is really in the orange maybe, because there is already like a Python-based way to input and output these files. Conversion scripts do exist, currently only in the Python implementation. We don't really have a proof of concept in any C++ based library. And we haven't done much work on the candidate specification proposal, primarily because we really need more community input on what the specification currently doesn't cover. So that's where we stand so far. So let me actually open this up. What questions do people have at this point about any of this, or comments or suggestions? I'd say the goal of this session is to tell you about this, but also to hear from you whether we're missing something really important in our roadmap, in the technical details of this insofar that I've told you about them, and so on. So I'm opening this up to questions and comments so far. Do you have a comment? Yeah.
I'll go there.
You can use this microphone. Yeah.
So I guess, hi, I'm Franco. Been involved here for some time. I guess the issue that I would like to point out is we're trying to do this community-driven, and we're doing as much as we can. But there's two communities we're talking to, and the two communities are responding in slightly different ways, in the sense that there's a community of users, and they're all like ready to go. Right? It's clear that everyone had challenges in transforming from, Ematrix to other toolboxes or DiPy, and it's a challenge to, if your colleague does the analysis in one format and you do the analysis in the other format, coordinates and everything are different. But the toolbox developer community, they've been dedicating years and years to their software. It's optimized, it works, they know it very well, and that's a different stake. So I guess the challenge that we would like to work with the open science community, how do we involve both of them? What type of incentives, or what type of maybe a shout out to the project would be fantastic for us. That you guys want it. I mean, no one said no. It's just that everyone is busy, and when you need to write software, it takes time, right? So this is, I think, for me at this point, this has grown fantastically, even though it's not funded at all. But we do have a challenge of finding the time for the developers of the various toolboxes to engage with us. And it's a question and a comment. I don't know what it is, but yeah. Yeah,
I'll raise one thing that is also kind of a challenge that we've faced, and that one thing that I think would help is full-featured C++ implementation of this thing that stands alone from the existing Python and JavaScript implementations. That would make it easier. We've been told by tool developers that would make it easier for them to incorporate it into things like Ematrix and DSI Studio and so on. My guess is that for a skilled C++ programmer, this should be a finite amount of work, let's say, of not large amount, but estimating software effort is really, really hard. And we've had 2 students already working on a C++ implementation, and we still don't have a C++ implementation that, say, Ematrix can just grab off the shelf and put into their software. So if anyone here in the room loves C++ and reading and writing files, what a beautiful project. With potentially really good impact for the community. Other language implementations could also be helpful for demonstrating advantages, but also limitations of the specification, right? We don't know, because my brain is pretty Python-centric. In Python, this works pretty nice, but I have no idea if this would run into just like obvious stumbling blocks in other languages. I know there are in the room fans of other programming languages like Julia. Yes. Maybe producing a little Julia prototype of reading and writing these files and just checking, oh, does this run into like really obvious, like, oh yeah, there's this thing that Julia just refuses to do that you assume that a programming language should do, but really, and C++ is where we're really worried. What? Yeah, Julia can do anything, of course. No, and I think Julia's, the problem is also Julia is really similar in a lot of respects to Python in terms of, C++ is quite different, but Julia is going to be pretty similar. It's also this kind of high-level scripting language like Python. The fact that this works in JavaScript is encouraging because they're technically quite different. So that maybe addresses. No, I agree with you. It's been very hard. People are of course very busy developing all these tools and stopping to say, oh yeah, let's shift over into. And people who develop tools think that their tools, myself included, are really great. So why change this particular fairly fundamental aspect of this? Other questions, comments? Yeah.
It's kind of quite general, I guess. Everyone in the room here is probably very proficient programmers, whichever language they choose. And then there's a lot of us who are users and noobs, and I feel like these platforms and toolboxes and pipelines are beautiful, but if you're not initiated, even the documentation that you think is completely idiot-proof, it's not. And so it's hard sometimes to be someone trying to adopt these best practices without someone holding your hand, which is obviously not practical. So yeah, I guess just sort of more of a thing of please really get some noobs to user test everything you do so that it is actually accessible to the whole community and not just those who are already excellent at what they do.
Yeah, great comments. I'll just repeat the question for those in the room or in Crowdcast that haven't heard that this was a request to make whatever implementations we make of this consider the needs of folks who are not super proficient software engineers, rather users of the tools that want to use it in research, say, settings to make both documentation and usability accessible to beginner programmers. The word noob was used, so I feel comfortable using the word beginner. I think right now I'm thinking also about providing examples, and so in the demo you'll see a few examples of how TRX is used. They're just not, I don't think are really, there's some really cool, Chris Rorden and his group have built these tools that just make this work really beautifully, and
It's always the dependencies though, that's what gets you. You're a beginner.
Yeah. So right now, so for example, right now in the Python, made an effort to just be sure it can be installed like pip install in a certain way. Most of the script that exists in the library are basically quality control, like convert TRK to TCK, or remove all of the invalid streamline or single point streamline or streamline that goes out of the volume, just to make sure you get a valid file, which is the first step. Get closer. Also, for example, in day-to-day life, TRK and TCK are used by everyone. They are very easy to use. Everybody like them. If you have a bunch of bundle, you just save 20 TCK. If you have connectomics, maybe you save 10 gigabyte TCK and you have a text file next to it that just tell you which one is which connection. And in the day-to-day life, that's probably fine. When you deal with your project, you know how to organize your data, and that's fine. But that's a very good example of TRX in bids. That would be useful to have something standardized, that you have a single file, and if you have a 10 gigabyte tractogram, maybe you can make it 4 gigabyte just to start off, and you don't want 20 files just next to it that just tell you what's in that. So that's the main use case of in bids we want something standardized, maybe for cold storage, long-term project, that's the first entry to TRX. So for example, if you have a gigantic tractogram and you have 20 bundle and 10,000 connection from connectomics, that's the kind of thing that can be hidden in the data per vertex, data per group, and like classically if you use TRK, I don't know if some of you are familiar with connectomics and TRK, some people will hide in data per streamline integer that say 1, 2, 3, 4, 5, 6 in the data per streamline to tell you secretly that this is the first connection and this is the second connection and third connection. Well, in TRX, this is a bit more explicitly used in data per group. If you have bundles, you can say this is the AF, and in that file you get all of the indices for the AF. You don't have to have a text file next to it with the indices and maybe another text file that tells you the name of the lookup table of each of those bundles. So like that's kind of the idea for TRX. Like I would say the entry point for a lot of people would probably be a converter to bids or TRK, TCK, 2 bids kind of scenario. And then like Ariel, for example, in PyFQ, when there's some things online that you want to fetch a bundle, you want to download from a cloud one bundle, you don't want like 20 text file laying around on your server, maybe have just a 10 gigabyte file of like all of your subject, and you have all of the which streamline is to which subject, or maybe which bundle is accessible in one file. So those are kind of high level. It's kind of hard to imagine yourself switching from TRK to this overnight. But that's why I think the toolbox has a few converter tool verifying that everything is valid, and how to generate a TRX from scratch. So like I could actually show that.
Can I show the demos here and then we'll switch?
Yes, yeah.
So I mean, we've talked about these cool demos. So let me just show a couple of proof of concept things. Here, okay, so this is something that Francois just mentioned. This is a cheat because these are multiple TRK files at the moment being read, but this is uses NeView in order to display data from a large data set. This is large data sets is publicly available on the cloud. This is the Healthy Brain Network data set, and using NeView, we can sort of read individual bundles into a viewer here and sort of select which bundles we'd like to view. This is because of the magic of the internet. You can view very large amounts of data pretty quickly, all in the browser here in this case. Here, it's reading it down. And the reason I feel comfortable showing this, even though it is a cheat and all this data is saved in TRK, is the fact that the underlying tool, NeView, that like I said, Chris Ward and his team have developed, already supports TRX. So this is a different kind of demonstration. This is really cool. This is a Jupyter notebook that you're looking at here, running on my browser, running Python code client-side on my browser using something called WebAssembly. So anyone of you can use this link in order to run all this code. And then what they've developed is a little tool that translates between the Python code running here and the JavaScript code for the visualization and sends messages back and forth. So one of the messages that we can send is, please load a mesh, load a TRX file, in this case a TRX file that's somewhere on the internet, and show it to me here in this viewer. So this is actually, this is not a cheat anymore. This is a real TRX file that's being displayed here. Maybe I should restart this and clear all the outputs so you can see the sequence of events that led to this. It's Python code that I'm running in Jupyter, so those of you familiar with that, this is the code is being sent to Python and read. Initially, when I create this NeView object, it's sitting here waiting on the images, and then I can, in subsequent code, I can tell it add a volume to this image, and then add my TRX, and then set the clip plane so that you can see the TRX. So this is a neat tool. The amount of code here you can see is not very, very large, and something that we can already use TRX to do, visualize, interact with this kind of bundle-based tracks.
There's already like a few tools in different language, and like you said, like having user to try them is very important, because we are often in our tiny bubbles of things working on our computer, and then as soon as it goes to a different computer, it doesn't work. This is a good example, because even if you didn't have Python installed or anything, that would work like in the browser, which is like a common lie that we have in the workshop. It's like, all you have to do is install Python, and then we can start a workshop, and then it takes 4 hours until everybody has Python running. So that's a good example of like entry-level tool. If I could connect my computer. I know most people here probably don't. Let's see if this works instantly. Almost. Wrong screen. Let's see if I can mirror this. Okay, so I assume most of you are not like fans of looking at code, but like it's just to show that like we have like the basic workflows for. Yeah, I should increase the font size. How do I do that on this keyboard? Yeah, so we a little bit more. So it's just to say that we have like basic script to do supernumeration. So this is like the Python library. It's not meant to be tools like in DIPy, like generate like tractography and things like that. It's more like, what if I have 20 big tractogram that are 1 gigabyte each, and I want to concatenate them? Well, we have a script for that is memory friendly. Even if you have 20 10 gigabyte tractogram, it's not going to take any RAM, but it's going to take 200 gigabyte of hard drive, because TRX is not actually loading stuff in memory. It's a memmap, so it's using the hard drive directly. We can convert tractogram from every common file type to every other common file type. And we work with other people to make sure that it's always like in the right space. There is no invalid coordinate. There is nothing like wrong with the file. Also generate TRX from scratch. So this is also difficult. Let's say you have a CSV file that are just laying around, and you want to just generate the TRX from scratch. You have the possession, the offset, you have data per streamline, you have a FA per bundle kind of thing, and you want to generate your own TRX from scratch. It's a big script, so like there is a lot of parameter. I don't know if it's possible to see. There's a lot of parameter, because you can set like the data per vertex, data per streamline, the groups, what are the data type you want to use. So there is obviously a lot of parameter, but you can take like your 20 file and just put them all together at once. Also validate TRX. Is it currently valid? Verify if it matched the header of a FA, for example. So if you have 20 files and you want to make sure that they are registered in MNI, and you want to make sure that all of your TRK and TRX fit the T1 from MNI, you just do star.trk, star.trx, mni.nifty.gz, and it say all of the header match. It checks the affine, it checks the dimension, it checks all of those things. So those are really like basic checks of quality control. So if one day we want to make sure that MRTrix write the TRX the right way, or if DIPy write TRX the right way, we have this toolbox that kind of agnostic to just take them all and just compare them together. Small example, you won't see the command from here, but I could zoom. Does it work? No, whatever. So here the command is just like visualize overlap between a TRX and a FA. And it's just a simple quality control that show me the streamline in RASMM. I don't know if you see that at the top, but it's like in wall space. And it shows the coordinate, it shows its overlap. Then when I quit, it's going to open them and also show it in voxel space. So like it verified that it overlapped in all of the different spaces that we commonly have streamlined. So like if you do registration, did it work? Those kind of questions. Is it equal to the TRK I had before? So those are all quality control scenario. And that's the last one in VoxMM. We also have like all of the basic function. I'm going to try to zoom in here. So obviously there is a load and save. That's very simple. But let's say I have a gigantic TRX. What is this weird file I'm talking about here? It's a file that's currently 2.3 gigabytes. If I convert it to TRK, it's 6 gigabytes. And if I convert it to TCK, it doesn't seem that big, but we have to remember that we just lost all of the data per streamline and data per vertex. So that's why it's smaller. You just lost most of the data. And like Ariel showed earlier, like what's in that file? Can I zoom? No, I cannot. I'm going to go in this one. What's in that file? It's very simple. You get all of your position, and cool thing, we can control the data type of the position and put float 16, so we don't waste any space by having the wrong data type. Then you can go in data per streamline, and then we have what kind of algorithm was generated the streamline. So we have a bunch of 0, 1, and 2, and 4 to say, is it probabilistic, deterministic, GTI, for example. But instead of having float 32 as a data type, which would waste space, we have unsigned int 8 because we can control those things. So those are standard like information that you can put in. You can also put groups for each of the streamline. So in Python, we have the classic load and save, but you can also select. Like here's I have a small corner case for myself. Like what if I select 0 streamline? What if I select 1 streamline? What if I select 1,000 streamline? Then I can convert them between file format. You can see that like instantly I'm saving it to TRK and TCK, and it works. I can also save it as a TRX. I can pick up a bunch of streamline. I have a bunch of timer, but like you can see that we have the basic load, save, select a few streamline. We can have, there is some routine right here where I say, give me all of the streamline that have a certain commit weight, for those of you familiar with those kind of things, but it's filtering. And here it's give me all of the streamline that were generated by the algorithm number 4. In that case, it's probabilistic. And then give me all of the bundle that are in my groups. So if I just run that, actually I don't have to run it, but it basically took my gigantic file that is 6 gigabyte TRK, but it's actually 2.3 gigabyte in TRX. And in 5 seconds, it basically successfully extract just the bundle that I care about. And those bundles have a certain color too. So like it's a way of going and getting exactly what you want. If you were doing connectomics and you have the connection like 1, like free surfer, like 1 to 95, you don't have to load the whole 5. You can just go get those indices. It's written in the file. It's one zip folder. And you can also compress the zip. It can be uncompressed, so it's faster if you don't compress it. But if you compress it, that file would be 1.5 gigabytes. So you go from 6 gigabyte to 1.5, which is perfect for cold storage, for like storing in bids. All of your file are in one. It's 4 times smaller than before, even if you have million streamline, and you can get exactly what you want from it. So this is the classic kind of use case. And it's kind of hard to compete with TRK because TRK is used by everyone. People are getting very good at using it after like 15 years. Everybody know the workaround. So it's kind of hard to compete against 15 years of experience with TCK and TRK. And then you get a new file format that I claim do the same thing and more, but you're not good with it. So it's kind of the challenge also on the user side of going from something you're very used to something new, even if it does the same thing. Is there any question about either the implementation or usage? Yep.
Should I come up?
Yeah, if you want, or you can scream real loud. But
No,
probably not recommended.
Yeah, come use this microphone.
This one.
Come on, podcast.
This looks very great. So I mean, I haven't been monitoring any of the discussions. I'll be excited to go through and read them in more detail. Sort of naively then looking at this, the file formats that's been chosen, especially the data per streamline or the data per vertex, I feel like if I kind of squint and turn my head a little bit to the side, the thing that I see is something like a table. Especially especially those two, but even really some of the others. And my sort of understanding of the way in which this archive is structured is that the different fields, as it were, are sort of written to sort of separate files, and that there's a lot of work being done to develop ways of efficiently doing that memory mapping and efficiently doing that access. And I wonder if you had considered, well, if you sort of agree that that like tabular format is a way to think about that implementation, and then if you had thoughts about exploring some of the work that's been done to do these or get these same sort of advantages of really low memory usage, computational speed and efficiency with things like the Parquet format or the duck database format. I'd love to hear your thoughts on that, or I mean any other sort of these vector databases that are emerging in the data science community writ large.
Well, I can say for at the very beginning, I tried a Python implementation that was using the ZAR format, and I tried another that I forgot the library, and something that emerged very quickly from Emergent, which is based in C++, was that basically you don't want to include anything that is not pure math in a toolbox. So like ZAR, for example, was kind of cool, but mostly in Python, pretty complex. If you wanted to transfer that in C++, and like, it's kind of true that if you have FreeSurfer or Matrix or another software, and I say you have to include Boost in C++, for those of you that know like C++, like they would be like, I don't want to do that. So like, that's why we kind of reverted to this overly simplistic, I say overly, but like extremely simplistic organization. It's basically all you need is zip, and that's it, because after that you start a os.seek there, and you skip that many to get your offset. And that was the main reason why we did not push into more advanced, even though they probably work like better if you go on Amazon Web Services and you want to like fetch stuff across server, but they would require something annoying for people in C++ and more advanced language. So that's why we kept it so simple.
Yeah, I'll just add, that was the main motivation. It's just generality, minimal dependencies. Also, if you're interested in that kind of stuff, there actually is another kind of community where this kind of work is happening, which is the computer graphics community. And some of the file formats that I showed before rely on these really super cool innovations in computer graphics to do things very fast and very performant. But again, the dependencies become tricky to manage across, the widest possible spectrum of use cases. So that's considered.
Yeah, that makes total sense, and that like is that seems, to me that seems like an absolutely stellar reason. Part of why I thought about it though is, it seems like some of the tricky parts are right now the C++ implementation of it, and so that's the sort of thing where, for some of these other file formats, like a Parquet format, for example, right? Like so much of the effort that's gone into them is developing tools to read it in C++, in Rust, in Go, in sort of XYZ, whichever one you can kind of imagine. And so that's why minimal dependencies is really wonderful, but of course that means that there's...
You have to code it yourself.
Yeah.
Now that's our problem.
Yeah, that's an interesting good point. I have to digest that though and think how that would play out, and we'd have to have a discussion also with the potential customers of this, especially the developers of other tools. It could make a compelling argument, I think.
Cool. And like I said, I know nothing about all of the extensive discussion that seems like has already gone on. So I'd love to keep chatting about it. But
if someone from the C++ software like Matrix was here, I would redirect your question to them instantly because that's a very good observation. That for them they were like, they wanted a generalist kind of file format, so something that can do a lot of things but very simple, and a lot of file format that already exists are specialists, so like for visualization, or like what if I have a 1 terabyte file format, which no one has, but like still they want to handle it. So together we're like, oh, generalist file format and no import. But it's true that if we just took something that we could import, they could instantly use it. But that's a question, I guess, for them. Because in Python, I would pretty much agree with you that like if I just import something and it worked, like ZAR at first that I tried, I think you suggested that earlier. In Python, it was import ZAR. The community for that file format was all in Python. Basically worked instantly, kind of scenario. It communicated with server very easily, but they had no library in C++. So then we kind of abandoned this.
Parquet, I think you're right, Parquet is a good direction because it's got wide adoption across multiple language communities.
Yeah.
It's not like, in C++, it's not like Boost. It's not like 6 hours to build, and I imagine.
I'm not sure. Yeah.
I always say boost because that's my trauma from like my bachelor. It's like when you import something, it's like you take your whole day to just like build it and it never works.
Which, yeah, I mean, that's frustrating.
I assume it's decent. I'm just joking about it. Yep. That's a great observation. Yep.
Anyway, thank you.
Thank you for coming. Question related to implementation, usage, tractography. If you don't know tractography and you want to ask a question. Yep. Etienne?
Stay here, so I had maybe a more future question, which is if you have an implementation in C++ and that becomes kind of the, I would say, mostly used one or the most rely on, do you plan on porting the other implementation like the Python or other based on this C++ to avoid having multiple implementation of the same thing? Or you plan to have the same implementation across the different code? So do you plan on kind of reuse?
I think you just volunteered. Right? Yeah.
Well, I could say that it would be very nice to, the Python right now could be like the original TRX Python that's like, you do QC in that one, you can do quick scripting to just like verify it's all like in the right space and all of those kind of things. Use Python library to do the visualization. But it's true that even we could have another Python version that's like for normal people, that's like, this one is even faster, and we copy the C++ one, and we just use a wrapper. And that would be like the Python that you pip install. And the other one could be like TRX Python QC kind of scenario, like the original one that we verify fit the specification, and we just make sure everything match with that one, and that all the other are just, you git clone the one you want. If you want the C++ one, the Python, that could be secretly the C++ one, JavaScript one and the Pascal one or the Julia one. But I think that the one we have in Python right now is mostly for QC. So I think that should stay. And also it gives us an extra layer of testing because it's different people. So it's useful to have a pure Python version just for testing. Oh, yeah, sure.
Yeah, thank you. I take your offer too if you want to help us. But this is both an effort to define a standard for describing files and a file, right? So in a certain way, there's both efforts here. So that's what the discussion is about. Like, for example, some of the discussion with the Matrix folks, they like to read the files in a certain way, not in another way, and they like to write the files in a certain way, not another way. So it's a little bit. So there would be multiple versions of files.
In C++, yes.
Yeah.
Most likely the C++ that we would host would be very simple, like straightforward. And it's very possible that the FreeSurfer C++ could be based on that one, just read and write. But I know for a fact that Matrix was like, no, we cannot just read and write. We need to make sure that all of our script read and write all of the metadata and support lazy load and lazy saving and all other things. So it's very possible that we have a standard C++ starting point, the original Python version, and probably, like you said, if we have a decent C++ implementation, I'm sure that it would be smart to just have a wrapper in Python for us. But we know for a fact that Matrix will have their own copy when they have one, hopefully. But we need a starting point. So if you know someone that knows C++ or is interested in C++, we are not looking for someone to do the full feature C++ implementation that does concatenation, appending, slicing, like read and write, and then like that's a starting point to make sure the specification work, basically. After that, we're going to see, because the specification right now is very decent in JavaScript and Python, but I don't know how zip and C++ work together. So, well, I hope it works well. We have a starting point that seems to work, but it's really about trying the spec. And if somebody complains hard enough, then maybe we're going to have the specification change.
And let's talk about incentives for the people that want to participate. Imagine how many studies use the Nifty file format. And tractography is perhaps the major file that is generated out of, I'm going to make a bold statement, that is distinct enough from Nifty and cannot be stored in Nifty, and we don't have something equivalent to Nifty. That's what we're trying to do here. So if this is successful, this can become the Nifty for tractography, and there's going to be citation to this work. So it's a good project to get on now.
Well, I think we can stop here. And if you have suggestion of usage, so if you are a user and you're like, I do that, can I do that with TRX? Well, that's a great discussion to have. If you know people that are specialists in MATLAB and you think a MATLAB implementation would be useful, all of these things like we can discuss. Especially just like read and write, like for example in MATLAB, it would be very nice to have a standard MATLAB implementation of read and write for TRX. Thank you.
Thanks for coming.
Yep.